What if, at this moment, we are not alone? 120 light-years from Earth, orbiting a dim red star in the constellation Leo, there exists a world unlike anything in our solar system. A world where oceans might lap against alien shores, where clouds might drift through skies tinged with hues no human eye has ever witnessed, where life, real extraterrestrial life, might be breathing, growing, evolving. The James Webb Space Telescope has detected something on this planet, something that shouldn't be there. A chemical signature so unlikely, so specifically out of equilibrium, that every conventional explanation falls apart under scrutiny. The atmospheric composition points to one conclusion with overwhelming statistical confidence: biological activity. Today, we journey through evidence that challenges our cosmic solitude. We examine data that suggests we may have finally found what humanity has sought for millennia. Prepare yourselves. We begin. In September 2023, astronomers analyzing data from the James Webb Space Telescope made an announcement that sent shockwaves through the scientific community. They had been studying K2-18b, a planet 8.6 times more massive than Earth, orbiting a cool red dwarf star. What they found in its atmosphere defied simple explanation. K2-18b is what astronomers call a Hycean world, a theoretical class of planet covered by a global hydrogen-rich atmosphere above a liquid water ocean. These worlds exist in a sweet spot, large enough to retain a thick atmosphere, yet not so large they become gas giants devoid of solid surfaces. They orbit in their star's habitable zone, where temperatures permit liquid water to exist. But K2-18b revealed something more, something extraordinary. The telescope's infrared instruments detected multiple biosignature gases simultaneously: water vapor, abundant, unmistakable; methane, present in significant quantities; carbon dioxide, exactly where the models predicted. But then came the anomaly: dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton, tiny organisms that form the base of marine food chains. It gives the ocean its distinctive smell. It's released when algae break down organic matter. In all our understanding of atmospheric chemistry, we know of no significant abiotic, non-biological process that produces DMS in detectable quantities. Yet, there it was, an unmistakable spectral signature at 9.1 micrometers, a molecular fingerprint that whispered one impossible word: life. The initial analysis suggested something even stunning. When the team ran statistical models incorporating all detected gases, their atmospheric composition, their relative abundances, and the planet's environmental conditions, the probability calculations pointed toward biological activity with 99.7% confidence. But the evidence forces us to confront an uncomfortable possibility. Are we truly witnessing life's signature across the cosmic void? Or are we seeing what we desperately want to see? Let's examine the evidence piece by piece, the way any rigorous investigation demands. Evidence 1. The water world confirmation. James Webb's near-infrared spectrograph detected water vapor absorption bands with unprecedented clarity. Not hints, not maybes, definitive spectroscopic proof of H2O molecules in K2-18b's atmosphere. The concentration suggests a humid world, potentially with 50 to 70% atmospheric water vapor, far higher than Earth's 1 to 4%. This is consistent with a planet hosting vast liquid water oceans beneath its hydrogen envelope. Water is life's universal solvent. Every form of life we know requires it. Finding abundant water vapor above a planet in the habitable zone checks the first box. Evidence 2. The methane mystery. Methane and carbon dioxide coexist in K2-18b's atmosphere, a combination that shouldn't persist together for long. In any normal planetary chemistry, methane, CH4, and carbon dioxide, CO2, react with each other under stellar radiation, destroying both molecules relatively quickly. On Earth, this reaction would eliminate atmospheric methane in just a few years. Yet both gases remain abundant on K2-18b. Why? On Earth, life constantly replenishes atmospheric methane through biological processes: bacteria in wetlands, termites digesting wood, cattle digesting grass, and countless other organisms. The methane we detect in our atmosphere is almost entirely biological in origin. Without life continuously producing it, our methane would vanish. K2-18b shows methane levels of approximately 1% of atmospheric composition, 10 times higher than Earth's natural levels. Something is actively producing it faster than chemistry can destroy it. Evidence 3. The carbon dioxide puzzle. The carbon dioxide levels tell another part of the story. At roughly 2.5% of atmospheric composition, CO2 exists in quantities suggesting active carbon cycling, not the runaway greenhouse effect of Venus, nor the frozen wasteland of Mars. The ratio of methane to carbon dioxide falls precisely within the range that biological activity on Earth maintains. This balance is delicate. Too much CO2 and the planet becomes a hellish greenhouse. Too little and it freezes. K2-18b's atmosphere suggests regulation, a planetary thermostat that maintains conditions within a narrow, habitable range. Evidence 4. The DMS detection. And then there's the dimethyl sulfide, the game changer, the molecule that transformed speculation into serious consideration. DMS was detected at trace levels, approximately 1 to 4 parts per billion. That might sound minuscule, but it's within the range of Earth's oceanic DMS emissions. More importantly, atmospheric models struggle to explain how DMS could accumulate to even these trace levels through non-biological chemistry. Laboratory experiments have attempted to synthesize DMS through purely chemical reactions under conditions similar to K2-18b. They've largely failed to produce meaningful quantities. Volcanic outgassing can create sulfur compounds, but not typically DMS in these specific atmospheric conditions. Photochemistry in hydrogen-rich atmospheres can create some organic sulfur compounds, but again, not this particular signature at these levels. But this is only one piece of a much larger puzzle. Deeper implications. As researchers dug deeper into the data, the picture became more complex and more compelling. The temporal stability argument. Follow-up observations spanning multiple transits of K2-18b across its star showed something remarkable. The atmospheric composition remains stable. Month after month, the same ratios of gases persist. This consistency suggests whatever processes maintain these atmospheric conditions are ongoing, active, and robust. If the biosignature gases resulted from some geological fluke or temporary chemical imbalance, we'd expect to see variation as these unstable conditions evolved. Instead, we see equilibrium, the hallmark of a system actively maintained by continuous input. The atmospheric pressure profile. James Webb's instruments can analyze not just what gases exist, but where in the atmosphere they concentrate. The methane and DMS show vertical distribution patterns consistent with surface emission sources. They're more abundant in the lower atmosphere, decreasing with altitude, exactly what we'd expect if these gases were being produced at or near the planet's surface and diffusing upward. This isn't definitive proof of oceans, but it's consistent with the Hycean world hypothesis, a planetary surface releasing gases into the atmosphere above. The missing ammonia. Here's where it gets stranger. Computer models of hydrogen-rich atmospheres in K2-18b's temperature range predict abundant ammonia, NH3. It should be there, created naturally through nitrogen and hydrogen combining in the upper atmosphere. But James Webb detected little to no ammonia. On Earth, certain microorganisms consume ammonia, converting it to other nitrogen compounds. The absence of expected ammonia, combined with the presence of unexpected organic compounds, paints a picture of an atmosphere being actively modified by something. The recent reinforcement. In late 2024, additional observations using James Webb's high-resolution spectroscopy mode provided further data. The team detected additional spectral features consistent with complex organic molecules, possibly methyl chloride, another compound that on Earth is predominantly produced by marine organisms. The evidence extends beyond simple gas detection into the realm of complex atmospheric chemistry that mirrors, hauntingly, the chemical signatures of our own living world.
To understand what we're seeing, we must understand the science of biosignatures, the detective work of identifying life from light. When starlight filters through a planet's atmosphere during a transit, when the planet passes in front of its star from our perspective, molecules in that atmosphere absorb specific wavelengths. Each molecule creates a unique spectral fingerprint. Water absorbs infrared light at certain wavelengths. Methane absorbs at others. By analyzing which wavelengths are missing from the starlight that reaches us, we reconstruct the atmospheric composition. But detecting gases isn't enough. We need to determine if those gases represent biosignatures, chemicals whose presence cannot be easily explained without invoking biology. Dr. Niku Madhusudan at Cambridge University, who led the K2-18b analysis, developed a framework for evaluating biosignature confidence. It considers detectability. Can we reliably measure the gas? Abundance. Is it present in meaningful quantities? Context. What other gases are present? What's the planetary environment? Chemistry. Can abiotic processes explain what we see? And stability. Does the atmospheric composition persist over time? K2-18b scores high on all 5 criteria. When fed into statistical models that compare thousands of atmospheric simulations, some with biological input, some without, the biological scenarios match the observations significantly better than non-biological ones. The 99.7% confidence level emerges from Bayesian probability analysis. It doesn't mean we're 99.7% certain life exists. It means the atmospheric data we observe are 99.7% more likely to occur if biological processes are active than if they're not. But science demands we consider alternatives. Could volcanic activity produce these gases? Partially. Volcanoes release water vapor, CO2, sulfur compounds, and even trace organics. But they don't typically produce DMS. More critically, the ratios are wrong. Volcanic atmospheres are dominated by sulfur dioxide, SO2, and carbon dioxide in much different proportions than K2-18b shows. Perhaps stellar radiation drives unusual chemistry in the upper atmosphere. Laboratory simulations have explored this. While photochemistry can create some organic molecules, producing DMS at detectable levels through pure photochemistry remains elusive. The experiments don't match the observations. Could the spectral features be misinterpreted? Perhaps we're seeing overlapping signals from other molecules that mimic biosignatures. This is always possible with spectroscopy. However, the James Webb data has been analyzed by multiple independent teams using different methods. The biosignature detections remain robust across all analyses. NASA's Jet Propulsion Laboratory, the European Space Agency's exoplanet team, and researchers at MIT have all examined the data. While emphasizing the need for caution, none have found methodological flaws that would invalidate the findings. This forces us to reconsider fundamental assumptions about life's prevalence in the universe. For decades, we assumed life was rare, perhaps unique to Earth. The Drake equation suggested intelligent civilizations might be scarce. But what if microbial life, simple, single-celled organisms, is common? What if Hycean worlds throughout the galaxy harbor biospheres beneath their hydrogen skies? The K2-18b findings have ignited an unprecedented surge in exoplanet research. The scientific community is mobilizing. Immediate follow-up. James Webb has allocated additional observation time for K2-18b in 2025. The goal, detect even more trace gases.
Scientists are particularly interested in phosphine, another potential biosignature, and searching for oxygen signatures that might indicate photosynthetic life. The Hycean Candidate Search. Astronomers have identified over 40 other Hycean candidates within 200 light-years. James Webb is beginning a systematic survey. If K2-18b isn't unique, if other Hycean worlds show similar biosignatures, the case for life becomes overwhelming. Next-generation technology. The Habitable Worlds Observatory, planned for the 2040s, will have the capability to directly image Earth-sized exoplanets. Rather than analyzing starlight filtered through atmospheres during transits, it will capture actual light from these worlds. We could potentially see cloud patterns, seasonal changes, even continent-ocean boundaries. The European Extremely Large Telescope, coming online in the late 2020s, will have a 39-meter mirror, 5 times larger than any current optical telescope. Its spectroscopic capabilities will allow even more detailed atmospheric analysis. What this means for us. Reflective music building to inspiring finale. We began with a question: what if we are not alone? The evidence from K2-18b doesn't provide a definitive answer. Science rarely does in one leap, but it provides something equally valuable: a direction, a path forward, a tantalizing suggestion that life's fingerprints mark the atmospheres of worlds beyond Earth. We know K2-18b exists, a super-Earth orbiting a red dwarf in Leo. We know it has water vapor, methane, carbon dioxide, and dimethyl sulfide in its atmosphere. We know these gases persist in ratios that biological activity best explains. We know the probability strongly favors a biological interpretation. What we don't know, not yet, is what form that life takes, whether it's microscopic or macroscopic, whether it's simple or complex, whether it's just beginning its evolutionary journey or is already ancient beyond measure. But we have the tools now to find out. James Webb has opened a new chapter in astronomy, the era of biosignature detection. What we discover in the coming years will reshape humanity's understanding of its place in the cosmos. Perhaps we are not the universe's only experiment with life. Perhaps we are one of countless worlds where chemistry became biology, where molecules learned to replicate, where evolution sculpted complexity from simplicity. K2-18b might be the first confirmed example, but it likely won't be the last. The universe is vast. The mysteries are endless. The journey continues.